Hey everybody, my name is Matt Brooks. I'm a research fellow with a group called the Citizen Lab. I'm also the overseas SOC lead for the SOC of a large energy company. The Citizen Lab is a group that focuses on researching a wide range of issues regarding internet freedoms, digital rights, but specifically I focus on looking at targeted malware intrusions that affect civil society organizations. So groups like journalists, activists, religious and ethnic minorities. So whenever I'm doing that work, I've started to really embrace using Redare or R2. Most of the code that I look at is what I call kind of Chinese nexus malware that is being used against the Tibetan diaspora. So that means most of the code that I look at is 32-bit x86 implants that are written and compiled in Microsoft's Visual Studio. And so in that case, whenever I start looking at a new file, I want to spend as much time as possible on the developer-written functions. I don't want to have to spend time looking at library code that's been linked in statically. Unfortunately, outside of using IDA Pro, that's a bit harder than it sounds. And so we'll walk through what that looks like. So I'm going to split the talk into three parts. I'll give an overview about what the problem is that I'm looking at. I'll talk about some of the implementations that I've built using the R2 pipe API, and then we'll see some applications where I've been able to use a signature format with pretty good success. So first, getting into the overview. To set this up, I kind of built an experiment. So I set up an old Windows development environment. I went old for two reasons. One, it's something that some of the malware developers that I see are still using environments that are this old. Two, I'm not looking at a version of Visual Studio that's so new that some of the tools that claim to have signatures built in aren't going to recognize them yet. So these are our older environments that have been in play for a long time. In this case, all I wanted to do was write and compile the standard Hello World program. And in this case, I did it in Visual Studio. I left all of the settings as default. The only thing I changed is that I compiled the code as C instead of C++. And I also compiled in release mode and didn't use debug mode to avoid the bias of all the code that gets added in whenever you do compile in debug mode, which is kind of a separate version of this problem. So with the executable here, I wanted to show what it looks like in a couple of different disassemblers as you might see it. So first, jumping back into the older version of IDA Free, using the source code on the left here, on the right is what you get. So the older version of IDA Free at least recognizes the main function, which is good. You can see the hello world string that's pushed onto the stack, and then you see a call to an unrecognized function. Now, for those who are used to using IDA, or using it kind of in pair with R2, a lot of people expect it to recognize standard library code. So you would expect it to recognize that printf function. Now, in this case, you can see the function is still unrecognized. And if you jump, so the screenshot down below that is if you jump into the disassembly for that supposedly unknown function, you start to see some calls to exception handlers, to error handlers, and that kind of stuff. Now, with experience, you can take a look at this disassembly, and if you know what the object of the Hello World program is, you know that that call is likely going to be print, because that's the goal. Also, if you were to start looking at the instruction, you just see that a lot of the calls are prefixed with the underscores, which are typically reserved for internal calls. Then you would start to realize, okay, maybe this is a library function. Now, imagine a different scenario where you're a mid-level kind of SOC analyst or a new researcher who's just starting out. Maybe you're somebody who can read, behavioral malware analysis reports. Some of the basic Win32 API calls that malware will use, but you're just starting to try to get in to understand, disassembly. And imagine that the string wasn't hello world. So think about now, either the time you're about to lose reversing this function, or the time that, the confusion that you're about to undergo figuring out what's going on. Fast forward to the newer version of IDA-free that was released earlier this year. Different scenario. In this case, main wasn't even recognized. All you get is being dropped in right at the entry point. And so you have to step through a bunch of compiler-generated or compiler-added code before you even get to something that looks like a main function. So in this case, again, you can see the hello world string that gets pushed onto the stack, and then call to an unrecognized function. Now, in this case, if you look at the function listing for the things that IDA's analysis picked up in this case, you can see that none of those were recognized by the standard signatures that people expect to work whenever you're using IDA. Unfortunately, if you remember looking at the source code here, you'll see I didn't implement any functions of my own. All I did was call a single library function with inside main, meaning the rest of the functions that are included here are compiler-generated code. So if you think back to the scenario that we just described a minute ago, still, really confusing for somebody who's trying to get into the game. Just to explore a couple of other disassemblers, Binary Ninja is one that's gaining a lot of popularity. If you load this up in there, again, you're going to get unrecognized main function. You get dumped in at the entry point, and then a bunch of other functions that are completely unrelated to what the malware developer or what the programmer was trying to do. And in Hopper, you get the same. Now, if we had loaded this up into R2, we would have, kind of showed the same thing as the older IDA-free version. So R2 will recognize main for you, but you're still going to see a bunch of functions that are added by the compiler, by Visual Studio, that go unmatched. So, with experience, that may or may not be okay, but it still kind of presents itself as a problem. Lastly, if we do jump to the paid version of IDA Pro, so if you have $1,400 US dollars to spend, you can see we do get a recognized main function and a recognized print function. So everything is good. So this is kind of the problem that I'm looking at is that, again, whenever I get a new file that I'm looking at, I want to maximize my productivity. So I want to spend time looking at the functions that were built by the malware developer, not the functions that are added in by a compiler. In this case, there are tons of different library code that might end up in a file that is compiled by Visual Studio. So there are tons of different versions of the Visual C runtime and the Visual C++ runtime. Aside from that, once you start thinking about Microsoft's foundational classes or active template libraries, tons of other library code that might get included, that space for the functions that get added kind of expands. If you think about expanding even further, OpenSSL, SQLite, zlib, different compression libraries, all these can end up, malware developers can use them statically linked code that will end up inside your malware sample, and even Borland's Delphi, still something that we have to care about. And so in this case, I want to be able to kind of have a little more control over the functions that I can write signatures for and build out without having a dependence on IDA's FLIRT technology. I want to be able to do this in a more freely or open solution. So to jump into some of the implementations, first, I do want to talk a little bit about IDA's FLIRT signature technology, just because that's one that exists and has been used for a long time, and it is a good approach to the problem. So the documentation for this is available online. So this is my understanding of what they're trying to do. The first step, given a library that you're trying to build these signatures for, is that IDA is going to take that and basically look at the first 32 bytes for every signature and mask out variant bytes. So bytes that represent relative memory addresses and that kind of stuff that may change, they'll mask out so that the bytes that you're considering are the core bytes to the function. And in that case, they'll store them in a tree-based structure. That way you're not saving the same bytes over and over. So if you think like function prologues that you might see at the start of a function, those may be the same for every function, so there's no need to store them each time. And so they store it in a tree-based structure, and then we'll branch out where the bytes start to change for each function. After that, using the sigmake tool, they'll process those patterns, and what they do is, moving away from that tree structure, they will store more of a bit array that represents where the different bytes have changed, and then they'll store the values of the bytes that have changed. And then after that, the signature files are compressed. Now, whenever you load a new file up into IDA, the way that it decides which signatures to load are based on the bytes at the entry point. And so it'll use special signature files, look at the bytes at the entry point, decide what type of environment that program was compiled in, and then we'll apply the correct signatures. After the fact, if you want to either use your own or change something, you can apply a different signature set. But again, that requires having the paid tools that are required to build those signatures. So earlier this year, I started exploring kind of the power of using R2 pipe. I had been using the R2 utilities for a while. I had been using R2 as a more static analysis tool. I really liked it a lot. And so I started to explore the R2 pipe, and it's fantastic. So there's a repository that I have on GitHub that I call R2kit, and it's just a bunch of different scripts that I've put together that make looking at malware within R2 easier. And so in this case, one of them is sigs.py, which is a script that I've built to kind of rebuild some functionality that's similar to FLIRT that'll allow me to rename functions and recognize functions automatically. After playing around a little bit, I came up with an implementation that I finally liked. So for every different type of signature I want to build, as long as the output of the algorithm can be an output string that can be hashed, I can build that as a generator, and then I can make and match accordingly. And we'll walk through some of the code snippets for what that looks like. I've come up with 3 different signature types that I'm using so far. The first is based off of Redaire's native signature format, which has been great. And then the other 2 are a little more experimental. One of them is dealing with string sets, so the strings that are referenced by a given function, and then also call chain gadgets, which are combinations of Win32 API calls that you might see in a given function. So we'll talk about each of these. So first, just to look a little bit about the structure of the file that I wrote, you can see there's a couple of different main classes in there. So first, the matcher class is what will end up being used if you're inside an R2 session against a target file. And again, this is going to take a location of signatures and is going to match them within the session. So it's kind of like doing a, auto analysis within a new target file using R2. The maker class, on the flip side, if I'm making new signatures against new library code, the maker class is what will get called, and again, it'll take a given location of either one or many different shared libraries, and we'll parse through the functions of each of those libraries and build the signatures given the signature type that I want to build. And then after that, on both sides, the generator class is used. And for every new signature type that I decide I want to build, I just need to build a subclass of generator, and then based on the extension or type that I pass it, that's the algorithm that's going to be used. So, even though I have different string types that are there, I kind of, can do a lot of this work in uniform, which has been pretty helpful. So for those who aren't familiar with R2's signature capability, I'll walk through just the basics of what signatures are. So this is a function, and this isn't a library function. This is a function from an older malware family called PC Client. The source code for this is up on GitHub. It's part of a repository by a developer that has a couple of different malware families in there. It also has the compiled code, so it makes it really nice to use for source to binary comparisons. Now, in this case, this is a function that is going to take binary coded decimal and convert it to ASCII. Now, if you Google how to do this, between Stack Overflow and Stack Exchange, you can find a bunch of different ways to perform this task. So let's say you were looking at this in a malware sample, and you thought that this was a pretty unique implementation, one that you wanted to build a signature for. Within the R2 session, so first, the command you'll run will be ZAF. So signatures, add a function, and I'll add the function name and the name of the signature that I want to create. And then after you create that, if you want to view it, you can just use the Z command. In this case, you can see the different components that are included in each signature. So I have the bytes, and again, you can see bytes, and you can see places where the bytes are masked, graph data, and then offset information. So for the purposes of what I'm doing matching-wise, I really only want to pay attention to the bytes component. And so in this case, again, R2 signatures capability goes ahead and handles that masking for us. So for relative memory offsets for bytes that may change, those bytes get masked out. The bytes that remain are the opcodes that are representative of the instructions, relevant constants, and that kind of stuff. So whenever I started exploring this, I thought, okay, if I just build the signatures for all the different versions of the library code that I want to write SIGs for, that should be fine. The capability is built. And so whenever I started, I built signatures for a couple of different versions of the C runtime. And whenever I was working against a target file in an R2 session, I would just pick up the right signature set that I needed, run that, and matching worked pretty well. So the process time was fine, the output wasn't too big, and the time that I spent matching was pretty acceptable. I mean, it wasn't anything instant, but it was fine. Now, once I started trying to expand that into more versions of the C runtime, or once I started adding like Microsoft's foundational classes, which is a really large library, performance started to kind of get a little bit. It wasn't what I was looking for, let's put it that way. In this case, just processing or building the signatures for the large libraries was taking a while, the output was massive, and whenever I started trying to match this library code against the target, even the matching performance was taking longer than I was willing to wait. So I needed a shorter way, something to increase the performance here. I'm not an R2 core developer, maybe one day, but I had been exploring the pipe, and so I thought there was something I could do still with that. So what I decided on was taking that signatures output, the bytes that we saw here, because it is just a string, hashing it. Once I hash it, if I handle the matching outside of the R2 native code, it just becomes a set lookup in Python, which is a really quick operation. So I put the code together and started that approach. So I took all of the redistributable libraries from Visual Studio that I had at the time, so I went from version 6 to 14, and ran the code over that and generated signatures, and I would start at the oldest library and move up to the newest one. And then against target files, I would start to use that. And the processing time took about an hour, so definitely still an upfront cost. However, the output was much smaller, and matching in a session against a target file was near instant, which was great. Just to keep going and get a little bit adventurous, I tried to expand that approach, so I took the entire System32 directory of a clean XP install, grabbed all the library code out of that, which was, I think it's over 100 different libraries, ran the processing, which, again, 2 hours, so there's definitely that upfront cost. However, when I started even trying to match on those signatures, the matching was still near instant, and the size of the output was still pretty acceptable. So I was happy with the performance overall, and it ended up working pretty well. So taking a look at what this looks like in the pipe here. If you remember, I said for every signature type that I wanted to build, all I needed to do was build a subclass of the generator class that I put in. And so in this case, I'll start at the first pipe command. Remember in the first talk, they described the difference between using command and command J. So everything I'm doing here is working with JSON, so I'll use the command J command for the pipe. And so first, the AFLJ command, it's an analysis command for the functions. I'm getting a list and returning them in JSON. So an easy way to get the full list of all the recognized functions from within a binary. After that, jump up here. So I'll iterate through the functions, and I'll issue that first command that we saw on the last slide. So I'll go ahead and Zignature add function. And then after that, remember, just Z would view the function, so ZJ is going to get me the signature back in JSON format. After that, I'll grab the bytes, and then again, I'm just hashing them. And then if that hash isn't something that I've already seen, I'll add it into a dictionary. I clear out the signatures after that. That way I make sure that I'm only dealing with one at a time. And then once the whole process is done, I'll return hashes. So using R2 pipe, this whole process of iterating through and creating everything I need has been incredibly easy. Really enjoying the R2 pipe API. Moving into some of the more experimental types. So when I think about string set hashes, sometimes a malware sample will come across my desk, and just by looking at the strings, it's really obvious that there is additional library code that's statically linked. And so this was from a malware sample I was looking at last year. Now, in some cases, the malware developer was nice. His internal name for the DLL kind of gave it away, sqlite 3. You can see other references to SQLite, and then other strings that are referencing database operations. Now, in this case, there are tons of different ways that SQLite can be added statically, and so using a Zignature, like a byte-based approach, wasn't going to work for this. However, once you start looking through the functions, just based on the reference strings, you can start to identify the functions that are library code. And so what I wanted to do was kind of exploit that fact. Just again, more detail what I'm talking about. If you run a command, so this is, I'm printing the disassembly summary for a function, the PDSF command. And so you can see kind of a condensed version of the function here. So this will ignore a bunch of the disassembly and just show you kind of the call pattern and the strings that are referenced. And so it's these combination of strings that I'm talking about joining together and then hashing. If this approach were standalone, the hashing part is a little over the top, but it's because I can do everything in a uniform format that I just go ahead and use the exact same generation pattern that I did for the signature hashes. And so again, a separate generator subclass. Whenever we look in the method, instead of getting a list of all the functions this time, I start with the list of all the strings. So I is for info. ZZ will get you all the strings. A single Z is going to get you the strings, I think, out of the data section. ZZ is all of them. And then J, I'm getting those back in JSON. I'll go ahead and jump through and iterate through each string if it's type that I'm considering. AXTJ, it's an analysis command. I'm getting the cross references to that string. And then I loop through them. And if the cross reference is from a function, I'll add that into a dictionary. After that, I'll loop through that dictionary, go ahead and hash the strings once I join them together, and then return those hashes. So again, this is a pretty experimental method, but as I started thinking about the way that I was identifying SQLite code anyways, I thought the method made sense, and it's worked pretty well. The last method that I was hoping to have finished before this talk, but unfortunately life got in the way, so we'll pop this in the future work section that I can start on as soon as I get back home, is looking at call chain hashes. So again, an experimental method that's pretty similar to string sets. And in this case, if we look at, again, PDSF, so I'm printing the disassembly summary for the function. And if you take a look at this, you can see if you look at the calls for that function, it's not calling anything that's statically linked. It's not calling any other developer functions. It's just calling 3 functions that are imports that are used to interact or query the Windows registry. So in this case, without spending time walking through each different instruction, you kind of know what the function's doing. The bottom screenshot I have here are some of the more commonly known, what I call gadgets, that you can look for in a function. So enumerating processes, searching files, each of these things has a set of Win32 API calls that you expect to see together. Now, these are some of the easy ones. I'm working on code right now that's kind of my start for this, which is designed to loop through larger directories of files and kind of aggregate different function call chains to find either edge cases or other useful gadgets that maybe weren't coming to my mind, so I can get all those things together before I keep working to build the generator. Now, to move on and see just a little bit about how some of these have been applied, I thought about applying these earlier this year. At the Citizen Lab, we're working on a case, again, a campaign that we tracked that was targeting a bunch of different groups within the Tibetan diaspora. Now, most of the tools that the actors behind this campaign were using were pretty simple. A lot of them stemmed from openly available implementations. But there were two versions of a really basic PowerShell dropper that gave me a good comparison point here, because it looked like the developer had compiled them in two different versions or two different development environments. So if we look at the first dropper, this was compiled on 15 January. If you look at the PDB path, I make the joke that he was at work when he was building this one, because the second one we'll see here was on an older development environment, so that must have been his home environment. He was using the new tools at work. And if you look at the versions of the Microsoft Visual C runtime that he's linked to, version 11 is Visual Studio 2012. If we parse out the PE header, just to kind of corroborate that, we can see that the major linker, again, version 11, so pretty consistent there. Once I loaded this up into R2 and used the signatures that I built, you can see I'm already matching on library code down to the right version, which it was actually a little bit better than I expected. The signatures had worked. When I went in and started comparing these, it was definitely the output that I expected, and it was down to the right Visual Studio version. Fast forward 2 weeks, again, I said we came across another version of basically the same sample. In this case, if you look at the debug path, Homeboy jumped back to Visual Studio 2005, or at least set that in the default. And if you look at the libraries that he's linked to, version 8 corresponds to Visual Studio 2005. In this case, again, if we parse out the PE header and take a look, the linker version is still 8, so all checks out. And as I start matching on things, going back to even the older versions of Microsoft's foundational classes. So again, between two basically similar versions of the same code base, I'm already able to match out library functions down to the right versions of different libraries. Oh, sweet. Thank you. Thank you. Jumping ahead to see the string set signatures applied, this was a case, a friend of mine in Hong Kong last year forwarded me. This was a copy of a spear phishing message that was used just before the chief executive election in Hong Kong last year that was targeting members of the pro-democracy movement in Hong Kong. Now, had a potential victim click the link here, which looks like it's a document, this actually walked through a pretty lengthy infection chain, but the final payload was the one that I was talking about that had a bunch of SQLite code that was compiled. And so it was a much larger payload. Whenever I loaded that up and used the string set hashes I had built, you can see all of the SQLite library code that I matched up, again, down to the version number. So the way that I'm doing this is whenever I start generating signatures, I start from the oldest version and move forward. So if a function hasn't changed across versions, the signature you'll see will be for the oldest version where that exists. So I was able to match out a ton of different functions that were going to end up being library code anyways, that no other tool that I had access to was going to be able to match. Now, I highlighted some of the function sizes here because you see some of them are small, like 42 bytes, 52 bytes. And these are some of the edge cases that I need to consider. These are smaller functions that really only have one string that they're cross-referencing. Now, in this case, because I'm working against a single sample with a single set of library code, I know that my match is okay. But if I try to expand this programmatically, matching a library code just based on a single string isn't quite a sound approach. So there's definitely some stuff that I need to think about there and some edge cases to explore. But overall, the approach worked quite well, and I was able to kind of ignore having to really look at this code in depth and just recognize and see where it was used. And again, just to show the stuff that I'm matching on, this is one of the functions that I matched that was in the malware payload. And then this is the same function summary from the SQLite 3 library. So again, doing this using PDSF, so print the disassembly summary for the function. And you can see the strings that I'm talking about here. So it's just combining those and hashing them. It may be a better approach to use kind of a masked or sanitized output of the entire PDSF output. That might be something that I consider as I start working on the edge cases. But for now, with the small domain that I'm working in, just the string sets had worked pretty well. So, I'm definitely not ready to stand up here and say, the approach is perfect. I've built something that's better than FLIRT. Not even close, but I think the approach is still pretty sound, and it's one that's open, and it's one that I'm really happy about, and one that I'm going to keep jamming on. So some of the future work that I have, one is kind of handling better names for library functions that aren't exported, because whenever I'm loading these up to generate the signatures right now, I'm not handling like debug information well or anything. So for functions that are exported, those get named. Anything else, the signature is more of kind of treating it like a tag, the fact that it's library code. For the Zignature hashes, because I am really happy with that one, that's not as experimental. I'm looking to expand some of the signatures that I have available. So a couple of newer versions of Visual Studio, and then moving into also looking at debug versus release mode whenever you compile code, just to see if there's something I can do there. After that, finishing up the call chains work. So before I build that generator, I want to spend some time analyzing different function level call chains that you see within malware. There's a lot of academic work in this space, but most of it is focused on using all of the Win32 API calls that you'll see across an entire binary to classify it. As far as I'm aware, and if you know of something else, I'd love to talk about it, there's not a lot of work done looking at this at the function level, kind of in aggregate. So finishing up some of that. As I mentioned, with the smaller functions or with the call chains, I need to spend some time polishing off the edge cases. And then I'd like to move this and package it outside of the repository that I have it in right now. Right now, the sigs.py script is coupled with another utility script that I have in there, and things are, again, kind of coupled together. But I would like to split this off as a separate project, maybe get it packaged within the R2 package manager, and also write the code to so that people who are using either Binary Ninja, Hopper, or other disassemblers can get a scripted output for their disassembler of choice and load that up in there, and not just keep this only to R2. And then lastly, compatibility with Python 3. I just write 2.7 off the top of my head, and I know that there are many in the room that will absolutely hate you for that. So I promise I'll get better at thinking about Python 3. And so that's all the content that I had put together to talk about. I know we're trying to, I think, gain up on some time here also. There's about 7 minutes left on the clock. So with that, the code is available on GitHub. I'm around here for the rest of the day to talk. I won't be here tomorrow. I have to fly back home. So if you want to talk about the approach at all, or if you've got feedback or tips, at some point today, I'd love to have a conversation. So that's it. We can. I didn't know if you were trying to make time back up.
I have a question, Matt. Sure. I really love the talk. I think it's really interesting, this addition to the Radar project. Is Citizen Lab doing some large-scale analysis on big data sets of binaries at the moment?
Nope.
Because I guess it could be a nice idea to have a leak.
It would absolutely be, yeah. We are not doing that. It's definitely on the list of stuff that we'd like to focus on. Mm-hmm. The list of development tasks that we have is, I'll say, large to say the least. So no, it's not something we're doing at the moment, but it would be a good approach.
I'm thinking on a scenario when you have a big data set and you can combine this implementation that you did with Elasticsearch, for example, and it's easy to figure out what you have to pay attention for.
Sure. For sure, yeah. It's not something that we're doing at the moment, though.
Congrats.
Yep. Right.
More questions?
Thank you. I would like to ask, you mentioned call chains and trying to classify or make signatures from call chains. Are you aware of the concept of system call dependency graphs or generally dependency graphs, taint analysis, and stuff like that?
That's a negative, Ghost Rider. But if you'd like to teach me, I'm happy to learn.
Yeah, well, basically it's a graph-like approach which investigates the dependencies between, for example, system calls or library calls and stuff like that. And it can be done on the function level, okay, because there's no reason not to. And it's a bit more. Why I'm mentioning that it's a bit more resilient against obfuscations.
Okay.
So, since you mentioned call chains, it's very similar to that, but instead of like a chain, it's more of like a tree or a graph.
Okay. No, it's not something that I'm familiar with, but it's definitely an approach that I'll spend some time looking at if it's something that would be better.
I'm sure that if you, I know that there's been some research done on that on, I think it was Berkeley, the Berkeley security labs, and
okay.
So I'm sure you could find some kind of research there.
For sure. Thanks, I appreciate it. Anything else?
Anyone else?
I can only see part of this. I can't see everything up there. It's bright.
Hello, Matt.
Yep.
Would you please reconsider again to use the Python 3, please?
Yeah, I absolutely will. It's just one comes to mind natively, and the other I'm like, I know there's something I'm supposed to do here. Fuck, I'll do it later. I will spend some dedicated time and get everything compliant, I promise. Yeah, cool.